the question you obviously ask is then, how do we work out what those coefficients are? How do we work out in the general case what the CNs are? Luckily, we have the genius of Fourier, so us mere mortals don't have to sweat and lose sleep about this. So last year I really skimmed over the development of the expression for the coefficients, or how you evaluate the coefficients for the Fourier series expansion of a function. And I regretted that, because although it's adding in a little bit more mathematical subtlety and a little bit more mathematical complication, though hopefully you'll not find it too complicated, I think it really helps you get an understanding of just where these formulae are coming from. If I go back to first principles with this, certainly that was the feedback I got from the students last year, so I swore to myself this year I'd put in a little bit more detail. So here's our starting point. Okay, so we've got a function, arbitrary function, whatever way you wanted to draw it, whatever arbitrary function you want to think about. As a function of time in this case, but it could be a function of x, it can be a function of whatever variable we like. Arbitrary function. And we're saying we can represent that function as a sum, an infinite sum, it's a minus infinity, of basis functions. And in this case, our basis functions are complex exponentials. They're a nice compact way of combining cosines and sines. But we could have basis functions that were just sines, or we could have basis functions that were just cosines, or indeed we can have basis functions, and if we go back to from Newton to Einstein last year, we had functions that look like this, which aren't continuous sines, which are sines within the well, but go to zero outside the well, etc., etc. I'm not going to draw them all out. But what we'd have here would be, let's call our functions, our basis functions un. So we have unx. So this would be u1, this would be u2, etc., etc., etc. We could have the same approach to representing a function, except in this case it would be in terms of x, by adding up, basically, fx is equal to sum cn un x. Okay, so we can add up our various different basis functions in this case, which in this case our basis set we're using are those standing wave states in the infinite potential well. And we can, if I can move that to the side, we can represent our function in just the same way. It's the same idea. We have a set of basis functions or ingredients for an arbitrary function, and we add those ingredients in just the right way by setting these coefficients to just the right values to recreate that function. That begs the question is, how do we calculate these values? Note that these are in principle complex valued. They don't have to be complex valued, they could be purely real, they could indeed be purely imaginary. But when they're complex valued, it means that not only can you control the amplitude, but you can also control the phase. Because once we've got that complex term in there, we've got a phase. Whereas if they're just purely real, we're just controlling the amplitude. Have a think about that. Hopefully that makes sense. But let's go back to our more general Fourier series. A little detour was just in terms to show you that we're not restricted to these basis functions. We can use lots of different basis functions. Right, so the expression for the coefficients, I'll write it down first of all, and then I'll explain where it comes from, is this. Okay. That's how our coefficients are defined, right? So we're taking an integral over one period of the function. I'm going to simplify things, although in general, to make it as general as possible, we can have an arbitrary starting point. Let's set that to 0, just to make things simpler and more clear. So we have an integration over one period of a function multiplied by, for the nth coefficient, to work at the nth coefficient, then we've got the nth basis function. What this is called is an overlap integral. An overlap integral. Because what this integral does, is tells us how much of this basis function is in this function, this arbitrary function. i.e., tells us the coefficient required, how much of this do we need in this, which is exactly what this is. If we want to reconstruct this correctly, then we need to know the coefficient that tells us how much of the nth basis function we need to recreate our overall function. Right, I will go through, as I say, I'll go through this in the in-person session as well and take questions then. So that's an overlap integral. Now, before we go any further in terms of showing you where this comes from, we need to introduce an incredibly important topic. A really neat topic, and a topic that is going to save you hours and hours and hours of irritating integration, and that's called orthogonality. And you'll have come across the term orthogonal before when it comes to vectors. The two vectors that are orthogonal, they are, as you know, the dot product, the mutual dot product is 0. There is a strong link between that understanding of orthogonality and the understanding of orthogonality that I'm going to put on the board now in terms of the context of functions. Don't worry about that for now. Later on in the module, when we get onto matrix mechanics, which is 6 or 7 weeks down the line, maybe 8 weeks down the line, I will revisit this and show you that link between orthogonality of functions and orthogonality of vectors. I'm just flagging it up because you might be wondering, well, does this orthogonal term have anything to do with vectors? Indeed it does, but in a fairly subtle sense. Anyway, in the context of functions, so again, we're going to have a set of basis functions. Let's call that f subscript n. We'll make them as a function of t. It could be a function of x, it could be a function of whatever we like, but we'll make it as a function of t. So, the definition of orthogonality is that for basis functions within this set of functions, f subscript n, so we have f1, f2, f3, etc. On an interval a, b, then the two functions from that set, or that set as a whole, is orthogonal if this condition holds through. So let's call one fm, and let's call the other fl. Right, where these are just indices, remember, these are just integers. So this could be a first function in our set, the second function in our set, or the third function in our set, and the 15th function in our set, or the 19th function, whatever. They're just integers, they're labels for different functions in the set. This represents the complex conjugate, right? But remember, for real functions, the complex conjugate is the same as the function. Always bear that in mind. It's a question that crops up every year. For real functions, which have no imaginary part, the complex conjugate of a real function is the function itself. So if we're just dealing with real functions, then we'll just have that. More generally, and for issues related to normalization, and we'll get to normalization in a second, in the same sense as you did last year, and from Newton to Einstein, normalization of the wave function, we express our orthogonality condition in terms of the complex conjugate of one of the functions multiplied by the function, another function, not the function itself rather than its complex conjugate. Okay, so the orthogonality condition is this. We've got this integral. If when we compute this integral, if for m not equal to L, this goes to 0, then we say that the functions in our basis set are orthogonal. When m is equal to L, and only when m is equal to L, does this integral become a finite value, will be a constant. Okay, I'll go m not equal to L, this is short for overlap integral equals 0. M equal to L, overlap integral equals a constant. So, As I say, mathematically somewhat subtle, but mathematically exceptionally powerful. And once you get this idea of orthogonality into your head, it's going to help you immensely throughout this module and other modules. But this is our definition of orthogonal functions. It has, as I say, parallels with orthogonal vectors. We'll get to that later on. For now, we're just running with this definition, and you will use this definition in the workshops this week. And also I'll run through it again during the in-person session. So overlap integral equal to 0 if m not equal to L. If m is equal to L, then the overlap integral is a constant, some value. Right. Now let's see where we get the expression for the values of our coefficients telling us how much of each basis function we need to recreate, to synthesize, to build up our arbitrary function f of t. We'll start with this. We're going to do a little mathematical trick now called Fourier's trick, which enables us to get an expression for those coefficients we need to build up the function. It's very clever and very neat. What we're going to do is multiply both sides by e to the minus I, y minus, we'll see, y m rather than n, we'll also see, just bear with me, we're going to multiply both sides by this. So that implies multiply both sides, so then over here we've got sum from, let me just write it like this, minus infinity to plus infinity, cn e to the I n omega 0 t by e to the minus I m omega 0 t. Now what we're going to do is we're going to integrate both sides over a period. So let's do that. E to the minus I m omega 0 t f of t dt is equal to, well, let's just put an integral sign in front of that for now. Minus infinity, infinity, cn e to the I n omega 0 t e to the minus I m omega 0 t dt. Can you see that? Probably not. Yes, you can. Right. So do those steps again. We start off with this, which is our definition of the Fourier series, telling us how we build up a function from linear sum, or to use the other term in quantum mechanics, superposition of these basis functions with coefficients telling us how much of each basis function we need. To work out those values of Cn, that's what we're doing right now. So our first step in doing that is multiply both sides by e to the minus Im omega 0 t. So we've done at that step. Then we integrate between, over one period, both sides again. So we end up with something that looks like that, which looks ugly and messy, I'll agree, but we're going to see just how wonderful orthogonality is. We need to do one other step, which might cause you a little indigestion, but hopefully not. So take that. Now what we're going to do to this is we're going to change the order of summation and integration. Now you might think, well, how can we do that? A number of different elegant mathematical theorems that show that we can do that even for infinite series, but just really to convince yourself, you could, for example, have, instead of an infinite sum, you could have a finite sum of functions, similar type of setup. So say instead of n going from minus infinity to infinity, you just go n is equal to 1, 2, 3. You don't even have to need to use these basis functions. You could have sine nx, for example, and convince yourself that it doesn't matter which way around you do the integration or the summation, you get the same result. At least for a finite series. Extracting that to an infinite series, obviously issues of convergence, etc., and other mathematical problems, but just accept that what the mathematicians have shown us, that it doesn't matter which way around we do the integration and the summation. So that implies this same side as before. Let me get rid of this before it gets too confusing. F of t dt. That, I'll just to save myself some room, to make more room on the board, I mean, is going to be equal to, what we're going to do now is, as I said, change the order. So we've got this, and here's where it gets really neat. E to the I n omega 0 t by e to, let me write this in the other way, e to the minus I m, just so it's clear where I'm coming from with this. E to the I n omega 0 t dt. Drop the chalk. Right. So, this, we are saying our basis functions, our basis set, functions in that set are orthogonal. You might say, how do you know that? Well, we can show that's one of the things you're going to do in the workshop. You're going to see for sines and cosines and mixtures of sines and cosines, and that's what we have here. They form an orthogonal set. You'll see how that goes. You'll show that for yourselves. For now, just accept that our basis functions are orthogonal, which means that in this case, for this integral will go to 0 only, and would be non-zero only in the case where m is equal to n. And when m is equal to n, then we can work out what that value of that constant is going to be. So let me write that down. For m equal to n, for m not equal to n, this integral vanishes. For m equal to n, that integral equals t. And if you don't see where that comes from, if you don't see where the t comes from, for m equal to n, work it through, make sure you can see where the t comes from for this integral. If you still can't do it, get in touch and I'll give you a hint to point you in the right direction. So that means we end up with, no, we can get rid of that because we go cycling through all values, and the only value that gives us a non-zero answer is when m is equal to n, so Cm, and that non-zero answer in this case is t. So this integral is equal to Cm, which is the value of the coefficient associated with the nth basis function, times t. One last step. Let's rearrange that. And you may have noticed as I was going along, I should have said this, the reason we multiply through by e to the minus im omega 0 t is that we've set up our orthogonality condition so it's the complex conjugate of one of the functions multiplied by another of the functions. Which means that if our basis set is e to the I n omega 0 t, the complex conjugate of e to the I n omega 0 t is going to be e to the minus I n omega 0 t. And that's true for m, j, k, l, whatever index you want to use to label the basis function. Similarly, we can just now write this as Cn, doesn't matter what we call the label, is 1 over t e to the minus I n omega 0 t f of t dt. Now we can go back to putting whatever arbitrary start on this we like, so we can shift this along. As long as we do it over one period, we're fine. And that is equation 2,3 in your notes for the coefficients associated with the Fourier series expansion for a function. So mathematically subtle in some ways, I'll agree, but very, very powerful because we've exploited orthogonality to basically remove an infinite number of integrations, reduce them down to one integration, which has a very simple answer. It's just a constant, it was just t. And that importance of orthogonality will, you'll see it so many times throughout the quantum world. Okay, with that little insert to explain the coefficients in more detail, let's return back to the original video. I've talked about time, and I've talked about translation between time and frequency. So time and 1 over time, reciprocal time, let's put it that way. or between units of seconds and units of hertz. That's essential. But I also want to hammer home that we can have the same idea when it comes to space. We can talk about space and something called reciprocal space, which might seem a bit mind-blowing and mind-expanding and has caused lots of students many sleepless nights in terms of solid-state physics courses, which is where you'll encounter it a lot, reciprocal space. But actually, it's a core, like Fourier analysis, the mathematics sometimes gets tricky and gets subtle, but the concept is actually relatively simple. So let's explain what I mean by reciprocal space. It's the same as in terms of reciprocal time. If we think of frequency as reciprocal time, we can think of reciprocal space in the same way. So let's draw a simple pattern. Zebra crossing, pedestrian crossing, whatever you want to call it. Let me try and draw this so it's reasonably evenly divided. Let me just shift that in a little bit. That okay? Yeah, it's okay. Right. Here's our zebra crossing. That's a two-dimensional object, obviously. So let's do something straightforward and just let's take a line section through this. So we have a function that varies. Let's just put our axis down there. We have a function that varies between a high value in terms of brightness, let's say that way, and a low value. And let's say it's binary and it just switches between 1 and 0 depending on whether it's bright or dark. Etc. We have a periodic function, but a periodic function now in space rather than time. We could have that in time as well. We could have a series of pulses in time. But we have a periodic function in space. So we can write down, you know, what's the separation between here? Let me see if we can draw this. Let's say that this is L. Distance is 1 period. And let's say, for want of argument, that it's 0.5 meters. That's our period. That's our spatial period. We can call it L, we can call it lambda, whatever you want to call it. But that's our spatial period. What's our spatial frequency? Well, our spatial frequency is just 1 over that. So we have 2 of these per meter. 2 periods per meter. So 1 period here, 1 period here. Our spatial frequency is 2 per meter. Per meter. That's equivalent to per second, which is hertz. We've got per meter. So we're going from space to reciprocal space. We're thinking in terms of spatial frequency. So what? And what has it got to do with quantum mechanics? It's got a heck of a lot to do with quantum mechanics. Because you'll hopefully remember from last year, we also had this. K is equal to 2 pi over lambda. What's that? That's wave number. What this is a spatial frequency. And in analogous to angular frequency in terms of time, so we've got omega is equal to 2 pi f, what we have here is effectively an angular spatial frequency, which is where the 2 pi comes from. And because we're now thinking in terms of frequency, we can do exactly the same thing. We've got a repeating pattern, so we can apply Fourier analysis to a pattern in space as well as time. And that's exactly what another of the simulations at the blog does. Let's go and take a look at that. So we're going to actually let the computer do the hard work of calculating those coefficients for us. There are ways and means, as you'll find in the second workshop, in the second worksheet, of using computers to calculate Fourier series for us and to find out those coefficients. You won't get away with escaping those integrals entirely, though. You will have to do some of those Fourier integrals. But in this particular example, I'm just keen to get across the concept here rather than to have you sit down and laboriously go through the integrals. I want to get the concept across first, and then you'll find that there's a motivation and a rationale for actually doing those integrals if you understand why you're doing those integrals. So, the black line up here is the function, is our square wave function that I've drawn on the board. What we want to do is we want to synthesize that from Fourier components. At the moment, we've got one Fourier component. It's a cosine component. I've deliberately chosen the symmetry of this square wave so that we have a cosine component. Now, it turns out that for this particular function, we don't have any even terms. We don't have any even harmonics in our Fourier series expansion. Also due to the symmetry is that we only actually have cosine components as well. What we have is there's our first term. Looks like that. Our second term is actually 0. Not particularly helpful. Our third term, however, looks like that. Notice it's a negative contribution. You can have positive and negative contributions. The CNs can be positive or negative. Think about what a negative contribution, however, means in terms of phase. And think about what's happened here in terms of the wave. N equal to 4 is also 0. As I said, all even terms are 0. N equal to 5 looks like that. We're back to positive, and it flips back and forth between positive and negative contributions. Note, however, what's going on up here. The red is our Fourier series approximation, and we've just got 5 terms. It's already not doing too bad a job. Obviously, we've got some ripple, quite a lot of ripple, but it's already starting to get a reasonable approximation to the edges here. So let's keep adding terms. I'm just going to slide this slider up, and you can see that as we add more and more terms, we're getting a better and better approximation to the square root. Now, in this particular function, we always have the eagle-eyed might be able to see that we have some overshoot and what's called ringing. We have some oscillations that we can increase the number of components to infinity. We'll never thoroughly, completely remove that. We can get smaller and smaller and smaller and smaller. And just to show you how this does really connect into the quantum world, here's a sort of zoomed in version of our zebra crossing or our square wave pattern. And you can see this ripple, and you can see it decays off. You know, it's fairly high amplitude and then decays off towards the edge, away from the edge. Look what's happening here. This is actually an STM, a scanning tunneling microscope image, and as you'll remember, an STM is sensitive to the electron density, and it's mapping out that probability to density. It's mapping out that modulus squared of the wave function, and what you can see is the same type of ripple and decay as we have. And the reason for that is because in the real quantum world, we can't go up to, even if we wanted to, we can't go up to an infinite number of terms. We don't have an infinite amount of energy. We don't have infinite wave number. So that means we've got a cutoff in terms of the wave numbers, in terms of the spatial frequencies we can access. And that means instead of the electrons being able to follow this step perfectly and reproduce it absolutely as it is here, what we have is this ripple. So what we're seeing is something called the Gibbs Phenomenon, which is what we call this ripple and overshoot. But we're seeing it physically manifest right down at the atomic level, at the quantum level. This is a beautiful image. Okay, so that's the Fourier series approach. We can build up periodic functions from combinations of sinusoids with different amplitudes, frequencies, and phases. I did mention, though, a little while ago, that we could also use Fourier analysis for aperiodic functions. So how does that work?